my name is Logan LaRose, and this is my final project on swarm robotics. My question for this project was how to create an evolutionary algorithm that would produce the best collective group performance, where performance is measured by the distance traveled to the left. I broke this into an A variant, where selection was made based on the best average performance of the group, and a B variant, where selection was made based on the best individual performance in the group. The C variant was for a separate question, which I'll explain later. This project was broken into 4 phases. The first 3 were deliverables, which built the swarm, then the world, and then a fitness function. The 4th phase was testing. For the A, B, and C variants, this was done with a population size of 20 swarms with 10 robots per swarm that were evolved over 50 generations. The fitness values were the distance traveled by each robot in the swarm, and the fitness function rewarded distance traveled to the left. For the A-B test, the fitness values were collected and compared. For the C test, the standard deviation across each swarm was collected as a metric for capturing swarm consistency. Shown here are the final solutions of the A-B tests. You can see that the environment has 10 boxes in the way of only some of the robots. All robots have the same body, and robots within the same swarm have identical brains, hence why they move similarly. There is some slight variation in the direction of movement between the 2 variants. For variant A, the solution had to consider the whole group's performance, so the whole group evolved to account for obstacles that only the middle robots were affected by. For variant B, the wings travel furthest if they move straight, so the whole group moves straight. The results show how close these selection methods were at producing collective group travel distance. The orange and blue lines are plots of the average group distance traveled. Hence, the selection method favoring average group distance does better. In summary, this is a classic case of comparing apples to oranges. It does, however, provide a good sanity check that what is expected to happen does happen. That's what brings me to variant C, which looks at the consistency across each group. This consistency was measured via the standard deviation across the group's fitness values. This plot shows the average standard deviation of the variants A and B, and you can clearly see that B is more consistent. The next plot shows the most consistent swarms. Notably, variant B can achieve nearly 0 variation across the swarm's performance, which is very desirable for a swarm robotics solution. My goal was to capture cooperation of a swarm like a group of ants building a bridge, and that is exactly how I would push this further. This would be incredibly difficult and would require a more complex power sim world and also the ability for robots to innately sense one another, all of this being expensive computationally. But there is value in group effort, and it's centered around the premise that there are some tasks that a group can do better than an individual.